Section: Introduction. In this section, we discuss the significant role of the attention mechanism in modern machine learning. Attention helps create context-aware representations of tokens by mapping sequences to sequences. Traditionally, this process uses the softmax function to generate token representations as weighted combinations of values based on the data. However, softmax has its drawbacks, such as focusing too much on a few features and potentially missing other important information. Additionally, using softmax requires reducing data row-wise, which can slow down computations, especially with efficient attention methods. To address these issues, we propose replacing the row-wise softmax with an element-wise sigmoid function. We identify a key challenge with this naive sigmoid attention: it can produce large initial attention values. We suggest solutions to mitigate this problem. Our contributions include proving that our sigmoid attention method is a universal function approximator for sequence-to-sequence tasks, analyzing its regularity, and providing a worst-case bound for its Jacobian. We also enhance FLASHSIGMOID with our sigmoid kernel, achieving up to a 17% reduction in kernel inference time and an 8% improvement in real-world inference. We demonstrate that our sigmoid attention matches the performance of traditional softmax across various tasks and domains. We define our input sequence as a set of vectors and introduce 3 learnable weight matrices to compute queries, keys, and values. We replace the normalization function with our sigmoid function, which is applied element-wise. We discuss how to choose an optimal bias term and show that our approach works for any sequence length. We also explore the theoretical properties of our sigmoid attention, focusing on 2 main goals: confirming that a transformer architecture remains a universal function approximator with our method and assessing the regularity of our approach by calculating its Lipschitz constant. We establish that transformers using our sigmoid attention can approximate continuous functions with high precision, ensuring that our modifications do not compromise the architecture's representation capabilities. We provide a theorem that guarantees this universal approximation property for our method, outlining the necessary adaptations from classical transformers. Section Summary. In this section, we discuss the limitations of the traditional softmax attention mechanism and propose a novel sigmoid attention approach that maintains the universal approximation property of transformers while improving computational efficiency. We also analyze the theoretical properties of this new attention mechanism, demonstrating its effectiveness across various tasks and its ability to handle large input sequences. Section: Sigmoid attention layers can implement contextual mappings. In this section, we discuss how sigmoid attention layers can create contextual mappings. A crucial part of proving our theorem involves demonstrating that, even with certain constraints, a series of transformer blocks can establish a contextual mapping. This mapping uniquely connects each element of an input sequence to an output that depends on the entire sequence. This feature enables a transformer to understand and retain global context for each token, even if each layer only compares pairs of tokens. Later layers can then utilize this global context to accurately map individual tokens to their corresponding outputs, effectively approximating any sequence-to-sequence function. We construct the contextual mapping by adjusting individual transformer blocks, with each block designed to respond to a specific input token. By stacking these blocks, we can transform a transformer into an accumulator that links a given sequence of input tokens to a unique global index. This is achieved through a selective shift layer and can be approximated using traditional attention mechanisms. Although our method cannot directly replicate a specific shift operation, we define an equivalent selective shift operation that can be approximated by our approach. We demonstrate that our shift operation shares similar properties with the original, allowing us to use the existing proof framework to show that our theorem holds true. Our proof closely resembles previous work, with 2 main differences. To approximate our shift operation, we need at least 4 attention heads and shifts in both the query and key definitions, while previous work required only 2 heads and shifts in the query definition. However, this is mainly a theoretical aspect and does not impact performance. Importantly, Both architectures require a similar number of parameters for approximation. Next, we examine the regularity of our sigmoid attention layer, which is essential for understanding the robustness and optimization of the network. We quantify the regularity by calculating the Lipschitz constant over a specific set, which indicates how much the layer function can change. The local Lipschitz constant is determined by the spectral norm of the Jacobian at a given point. We establish a theorem regarding the regularity of our layer, defining the set of attention weights and scaled activation norms. If we assume the attention weights are bounded, we derive bounds based on the average squared norm of the input sequence, contrasting with classical results that depend on the largest value. Our findings suggest that if the input sequences are within a certain range, the Lipschitz constant of our layer increases at a controlled rate, and this holds even for unbounded distributions as long as the second moment is bounded. This is a significant improvement over previous results, which indicated that the local Lipschitz constant of our layer is much lower than that of traditional attention mechanisms. Section Summary. In this section, we demonstrate that sigmoid attention layers can effectively implement contextual mappings, allowing transformers to capture global context and approximate any sequence-to-sequence function. We also analyze the regularity of these layers, showing that their Lipschitz constant is more favorable compared to traditional attention mechanisms, indicating better robustness and optimization potential. Section: Computational complexity of sigmoid and softmax. In this section, we discuss the computational complexity of sigmoid and softmax functions, focusing on our hardware-aware implementation called FLASHSIGMOID. We note that memory speed has not improved as quickly as computation speed, leading to attention computations being limited by memory access times. To tackle this, we build on the ideas from FLASHATTENTION and FLASHATTENTION2, which enhance GPU memory usage to speed up attention calculations. FLASHSIGMOID employs a divide-and-conquer strategy, processing input parts in parallel to efficiently compute attention outputs in blocks. We also implement kernel fusion, combining the forward and backward computational steps into single GPU kernels. This reduces memory accesses and avoids storing intermediate activations in high-bandwidth memory, which can slow down performance. For the backward pass, we only keep the query, key, and value tensors, allowing us to recompute the sigmoid activation matrix without the need for extra memory, despite increasing the number of floating-point operations. This method ultimately results in faster execution times and better memory efficiency compared to retaining the attention matrix. We highlight that FLASHSIGMOID is faster and more memory efficient than FLASHATTENTION and FLASHATTENTION2 due to its pointwise nature, which eliminates the need for softmax normalization. Additionally, we reduce the number of kernel dispatches and avoid tracking intermediate variables, further cutting down on computation costs. We optimize the sigmoid computation on the GPU and find that FLASHSIGMOID outperforms FLASHATTENTION, even though the theoretical performance of sigmoid is slower than softmax. Our performance benchmarks on H100 and A100 GPS show a significant speed-up during inference and training, although real-world factors like tensor movement and other computations can affect these gains. Nonetheless, we demonstrate that FLASHSIGMOID can speed up training by over 53% and inference by a similar margin in practical scenarios. To validate our implementation, we conduct experiments across various domains, including supervised image classification, self-supervised learning, automatic speech recognition, and language modeling. We find that FLASHSIGMOID matches the performance of softmax while providing notable speed improvements. Our observations indicate that FLASHSIGMOID is effective for vision tasks and requires specific adjustments for language modeling and speech recognition to achieve optimal performance. Section Summary. In this section, we present FLASHSIGMOID, a hardware-aware implementation that optimizes attention computations by efficiently utilizing GPU memory and reducing memory accesses, resulting in significant speedups during both training and inference. We validate FLASHSIGMOID across various domains, demonstrating its effectiveness and performance parity with existing methods while achieving notable improvements in computational efficiency. Section: Ablations. In this section, we begin with ablations to understand the advantages of each component we introduced. To explore the model's behavior, we created a user-friendly auto-regressive language model training framework. This allows us to assess various attention components and validate the effects of layer scale, layer norm applied to the query and key, different positional embedding methods, and initialization values. To address large attention norms, we trained a single-layer auto-regressive transformer block on a specific dataset. We trained for a set number of steps with a batch size of 6 and a maximum sequence length of 4096, using a cosine learning rate schedule without weight decay. Initially, our model performed poorly with certain positional embeddings, which we believe was due to high initial attention norms. We observed changes in attention distribution and sparsity, which we documented in the appendix. To tackle these high norms, we proposed two solutions: using alibi to adjust the initial attention distribution or applying a negative offset to the attention logit bias based on sequence length. This adjustment allows us to use other positional embedding techniques effectively. Next, we examined the necessity of layer scale by measuring its impact on model stability. All models were trained with a specific positional embedding method, using a standard optimizer and a defined batch size and sequence length. We also tested various learning rates to assess sensitivity. We found that while layer scale slightly improved performance in one model, it had little effect on another. We then looked into the stability provided by layer norm applied to the query and key. Our analysis showed that both models were sensitive to learning rate changes without this normalization. However, incorporating layer norm significantly stabilized performance. In vision tasks, one model showed robustness regardless of whether layer norm was applied. We also explored multi-query attention, finding that both models performed similarly with or without multiple heads, even at a smaller scale. Regarding activation functions, we noted that various functions combined with layer scale and layer norm performed well in vision tasks. However, for tasks requiring precise sequences, some activation functions led to instability and underperformance. Finally, we discussed related work, noting a shift in large-scale machine learning from traditional softmax functions to richer pointwise Bernoulli conditionals. Our focus was on refining the model's internal mechanics by replacing the softmax in the attention mechanism with a pointwise sigmoid function. We built on previous research that explored different activation functions and attention mechanisms, but we found that their approaches did not yield expected performance without proper initialization and the use of layer scale.